In this quiet space of Dreamtime Science, we turn down the volume of the universe to hear its subtlest secrets. Let's explore the cosmos at the perfect pace for peaceful contemplation. You know, I've been thinking about energy a lot lately. Not just the kind that powers our homes or makes our muscles move, but energy itself, in its most basic form. There's something remarkable about how this invisible force is everywhere, quietly shaping everything from the tiniest atoms to the stars above us. I can't wait to share with you what makes energy so surprisingly simple, yet endlessly fascinating. If this peaceful blend of science and serenity helps ease your evening, consider joining our community of gentle learners. Share your favorite moment of scientific awe in the comments. Take this moment to settle in, wrap yourself in comfort, release the day's weight from your shoulders, and let your breath become as gentle as starlight. Close your eyes and let your mind drift backward through the velvet corridors of memory and imagination to a place where the hush of midnight is broken only by the gentle ticking of a clock, each tick a heartbeat of the universe. The room is dark, but for a thin line of moonlight upon the floor, and you, curled beneath a warm blanket, are poised to slip into a world where thought and wonder are your guides. Tonight, we begin with a question so simple and so profound it has haunted humans since the birth of fire. What is energy? Not merely in the way your body hums with wakefulness or grows heavy with sleep, nor just in the flicker of a lamp or the warmth of the sun on your skin, but energy in its most essential, elusive form, the invisible current that pulses through every atom, every star, every story ever told. If you listen closely, you can almost hear it, the soft, secret crackle that whispers through the wires in your walls, that surges unseen between the branches of lightning, that glimmers in the afterglow of a dying star. Energy, that ghostly currency, neither created nor destroyed, forever moving, forever changing form. It is the breath of the cosmos, the music of existence itself. Let us begin where imagination and reality intertwine, in the world of stories, of cinema, where energy is not merely a dry equation, but a living, breathing force. Picture the flickering green code cascading down the screens of the matrix, each glyph a sigil of possibility. In this imagined world, human lives are harvested as batteries, their bodies mere vessels for the production of power. The cityscape hums with a digital pulse, the air thick with the implied presence of energy, shapeless, unseen, yet all-consuming. In the matrix, energy becomes both literal and metaphorical currency. The machines, those cold architects of this manufactured reality, siphon warmth and vitality from their human captives, converting the spark of life into the juice that drives their empire. The film's vision is at once chilling and oddly poetic, a meditation on the omnipresence of energy, its capacity to animate, to enslave, to liberate. Yet, step back from the fiction and realize, the matrix is not so far from the truth. Every moment, everywhere, energy is in motion, cycling, transforming, unending and unseen. What the film captures in metaphor, science reveals in detail. The story of energy is the story of transformation, of potential becoming actuality, of what is hidden becoming manifest. To understand this, we must follow the thread back to where science first glimpsed the unity of matter and energy. Picture, if you will, a patent clerk in Bern, Switzerland, hunched over a cluttered desk in the pale light of a century gone by. His name is Albert Einstein, and he is about to write a sentence that will shiver through the fabric of reality, a sentence so simple it fits upon a postcard, so profound it reshapes our understanding of the universe. E equal mc2. Energy equals mass times the speed of light squared. With these 5 symbols, Einstein did more than just provide a new formula. He whispered a secret of the cosmos. Mass and energy, he said, are two sides of the same shimmering coin. What we call matter is simply energy in a particular arrangement, and what we call energy is matter set free, unbound, racing at the speed of light. Pause here and let the idea settle like mist upon a lake. The chair beneath you, the air you breathe, the neurons firing in your brain, each is built of matter, and within each atom a reservoir of energy slumbers, waiting to be awakened. Strike a match, and the chemical bonds in its head break, releasing heat and light. Feed your body, and the calories of food become the movement of muscles and the flicker of thought. All around us, the world is a theatre of energy's transformations, a grand ballet choreographed in silence and invisibility. And yet, though we know its presence by its effects, energy itself is curiously intangible. You cannot hold it in your hand or see it with your eye, not directly. It is the promise of movement, the possibility of change. In physics, we say that energy is the capacity to do work, the ability to move an object, to heat a substance, to light a bulb, to spark a neuron. It is a concept both practical and mysterious, defined by its consequences rather than its substance. This abstractness gives energy a peculiar magic. It is at once everywhere and nowhere, the thread that weaves together the tapestry of the universe. In every story we tell, whether of superheroes whose powers crackle and blaze, or of spaceships powered by impossible reactors, or of dystopias where energy is both weapon and prize, energy is the unseen protagonist, shaping fate from behind the scenes. Return now to the Matrix, that digital dreamscape where reality itself bends to the will of those who understand its code. In this world, Neo learns to see the hidden currents beneath the surface of things, to read the language of energy written in streams of numbers and symbols. The walls of the world become malleable, no longer barriers but clouds of possibility, awaiting the touch of a mind attuned to their true nature. This is not just science fiction. In a sense, all of physics is an attempt to do what Neo does, to peer through the veil of appearance and glimpse the machinery underneath. When Einstein wrote E equals mc2, he offered us a key to this machinery, a glimpse into the engine room of the cosmos. But why the speed of light squared? Why this dazzling enormous number, 299,792,458 meters per second, multiplied by itself, yielding a value so vast it staggers the imagination? The answer lies in the structure of reality itself. The speed of light, c, is not just how fast light travels. It is the ultimate speed limit of the universe, the pace at which causality itself unfolds. To multiply mass by c2 is to tap into the deep connection between matter and the very fabric of space-time, to see that even a speck of dust, if its mass were converted entirely into energy, could unleash a force beyond reckoning. Consider the sun shining in the sky, a constant silent presence, and its warmth is the result of nuclear fusion, a process where hydrogen atoms deep within the sun's core are pressed together with such ferocity that they merge, their mass ever so slightly diminished, their loss released as radiant energy. Every second, the sun transforms millions of tons of matter into light, into warmth, into the life-giving energy that bathes our world. That is E equal mc2 at work. Not just an equation, but a cosmic alchemy, or think of the atomic bomb, that terrible flower of the 20th century. In the instant of detonation, a small amount of matter is transformed utterly into energy, heat, light, shockwave. The devastation is not a result of chemical reaction, like fire, but of something deeper and more profound, the unlocking of the energy bound within the nucleus of the atom. Here, the unity of mass and energy is not only demonstrated, but weaponized, a sobering testament to the power of Einstein's insight. Yet in the day-to-day, we rarely see such dramatic transformations. Instead, energy flows quietly, invisibly, from one form to another. We eat, and the energy of sunlight, captured by plants, becomes the movement of our muscles. We flip a switch, and the energy of falling water or burning coal becomes the glow of a lamp. We dream, and the energy of chemistry becomes the dance of neurons, the flicker of consciousness. This flow, this endless transformation, is the essence of energy's dance. It is never lost, never created anew. It only changes its mask, slipping from light to heat to motion and back again. The physicists call this the law of conservation of energy, a rule so fundamental that the universe itself would unravel without it. In the world of the Matrix, the boundaries between dream and reality blur, but the laws of energy remain inviolate. Even within the simulation, the code must be written to conserve energy, to balance the books of existence. If Neo leaps impossibly high or bends the laws of physics, the system compensates elsewhere. The fiction is a mirror to the fact. Every action, every reaction is accounted for in the cosmic ledger. Yet, for all its omnipresence, energy remains elusive, a concept more easily felt than defined. It is the tension in a stretched spring, the kinetic rush of a falling stone, the quiet hum of a city at night. It is the potential locked in the bonds of molecules, waiting to be released in a flash of heat or a spark of light. In every case, energy is the story of change, of the possible made real. In popular culture, energy is often rendered visible, crackling arcs of electricity, beams of light, explosions of color. These are the signatures of energy in transit, the moments when its passage leaves a visible trace. But most of the time, energy works in shadows, moving silently through the world, shaping everything yet remaining unseen. Consider for a moment the world as you know it. Your body, composed of atoms forged in ancient stars, is a vessel of ceaseless transformation. The food you eat, the air you breathe, the warmth you feel, each is a step in the elaborate choreography of energy's dance. Every heartbeat, every breath, every thought is both a beginning and an ending, a moment where energy changes hands, never lost, only transformed. In the gentle dark of the night, as you lie listening to the distant murmur of the world, you are part of this dance. The electricity that powers your lamp, the calories that warm your blood, the photons that drift through your window, all are threads in the tapestry, woven together by the unseen hand of energy. And so, as we drift further into our exploration, let us hold on to this image. Energy as the silent, invisible choreographer of existence, forever present, forever changing, forever just out of reach. In science fiction, it is rendered with drama and light. In the equations of physics, with elegance and brevity. In both, it is the thing that makes all things possible, the ghost in the machine, the fire behind the eyes, the secret written in the code of the cosmos. Yet, for all our understanding, energy remains a mystery, as much magic as math, as much poetry as principle. It haunts our stories and our equations, our dreams and our discoveries. We have traced its pathways, measured its effects, learned to harness its power, but its essence slips through our fingers like water, always present, always moving, never still. As the night deepens and the world grows quiet, feel the energy that surrounds you, that fills you, that connects you to all things. In the next breath, in the next heartbeat, in the next flicker of thought, energy moves, unseen, unstoppable, eternal. The dance continues, and we, for a moment, are part of its endless, silent waltz. Out there, beyond the window, the city hums with hidden currents, and somewhere, deep in the code of dreams, the green symbols fall, hinting at deeper mysteries, the patterns and matrices that underlie all things. The story of energy is only just beginning, its true nature waiting in the shadows, ready to be revealed. If you lie back and close your eyes, listening to the world's quiet hum, you may sense, beneath the everyday, a pulse, a hidden rhythm in all things. This is the whisper of energy, threading through the tapestry of existence, ancient yet always new. In this gentle darkness, let us turn now to those secret patterns, to the strange, flickering realm where energy's true nature reveals itself not in the sweep of planets or the falling of apples, but in the flicker of the infinitesimal, where certainty dissolves and possibility reigns. The story begins at the dawn of the 20th century, when the world of physics trembled on the cusp of transformation. For centuries, energy seemed a reassuringly solid thing, a measurable property stored and spent in the gears of machines, the swing of pendulums, the warmth of fire. But as scientists peered ever closer into the heart of atoms, into the subtle glow of heated metal, they found their familiar rules trembling, then breaking. The comforting laws of Isaac Newton, so successful in guiding ships and predicting eclipses, began to unravel when applied to the very small. It was in the gloom of a laboratory, watching as metals glowed red and orange in the fire, that Max Planck first glimpsed the strangeness. Planck had set out to solve a puzzle known as the ultraviolet catastrophe, a name as dramatic as the dilemma itself. According to the classical theories, a hot object should emit infinite amounts of energy as it glows, especially at higher and higher frequencies. But this, of course, did not happen. The world did not dissolve in a flood of invisible, lethal energy each time a stove was lit. Reality, it seemed, was holding something back. Planck, with a mixture of desperation and inspiration, proposed a radical solution. Perhaps energy itself was not infinitely divisible. Instead, he imagined, energy could only be emitted or absorbed in discrete packages, tiny bundles he called quanta. Each bundle was proportional to the frequency of the light, its size dictated by a new constant, Planck's constant, a number so small it defies everyday comprehension, yet so fundamental that it haunts the heart of every atom. With this audacious idea, Planck did not merely solve the problem of glowing metal. He cracked open the door to an entirely new understanding of reality. Suddenly, energy was no longer a smooth, continuous river. It became a staircase, a series of abrupt jumps. A system could not possess any arbitrary amount of energy, but only certain allowed amounts. The universe, it seemed, leapt from state to state, skipping the spaces in between. This was the birth of quantum mechanics, a theory as unsettling as it was beautiful, a world where certainty and continuity gave way to probability and leaps. Here, energy is both wave and particle, both everywhere and somewhere, both fluid and quantized. It is a paradox woven into the very fabric of existence. To understand this duality, let us focus on the most familiar messenger of energy, light. For centuries, scholars argued over its nature. Is light a wave, like ripples spreading across a pond, or is it a stream of particles, tiny corpuscles darting through the void? The answer, as quantum mechanics reveals, is neither and both. Light sometimes behaves as a wave, diffracting and interfering, painting rainbows and shimmering on soap bubbles. But in other experiments, it acts as a particle, delivering its energy in discrete, indivisible quanta known as photons. Each photon carries a packet of energy, an amount determined by its frequency. When a photon strikes an atom, it can jolt an electron free, as in the photoelectric effect, a phenomenon that baffled the classical physicists, but which Albert Einstein explained by embracing the quantum view. Energy, then, is not a simple thing. It is a measure of change, a currency exchanged in every interaction. But in the quantum world, it is also a mark of possibility, a set of permitted transitions. An electron bound to an atom cannot reside at just any distance from the nucleus. It is constrained to certain energy levels, like rungs on a ladder. When it absorbs a photon, the electron does not drift gently upward, but vanishes from one rung and appears on another, higher up, an abrupt, mysterious leap. The energy of the photon must match exactly the gap between these rungs, or the transition will not occur. Thus, the color of light an atom can absorb or emit is dictated by the architecture of its quantum states. These quantum leaps are not like the graceful arcs of Newtonian physics, not the smooth, predictable trajectories of billiard balls or planets. They are sudden, discontinuous, and fundamentally unpredictable. We can know the probabilities, the odds that an electron will jump or stay, but not the precise moment. It is as if the universe rolls dice in secret, its inner workings veiled from our gaze. The implications are profound. On the grand scale, energy seems to flow smoothly, as in the flight of an arrow or the churning of a river. But beneath this surface, at the level of atoms and photons, it moves in sudden bursts, flickering between allowed states, never lingering in the forbidden spaces in between. The familiar laws of energy conservation remain, but now they are enforced in discrete steps, as though reality itself were pixelated. Consider for a moment the act of vision. When you gaze at the stars on a clear night, the light that enters your eye has travelled for years, decades, even millennia, crossing the void as a train of photons. Each photon carries a precise quantum of energy, determined at the moment it was born in the heart of a distant star. When it finally reaches your retina, it strikes a molecule, and, if its energy matches the gap between quantum states, it triggers a cascade of events, a quantum leap that ultimately allows you to see. Your very perception of the cosmos is built upon these ancient individual journeys, each one a story of energy measured out in the smallest possible units. Yet, for all its power, the quantum description of energy brings with it a sense of uncertainty. In the quantum world, the act of measurement disturbs the system being measured. Heisenberg's uncertainty principle tells us that the more precisely we know the energy of a system, the less precisely we can know how long it holds that energy, and vice versa. This is not a limitation of our instruments, but a fundamental feature of nature. It is as if the universe holds its secrets tightly, allowing us only fleeting glimpses, never the full picture. Energy, then, is not just a property, but a kind of potential, a spectrum of possibilities shimmering with uncertainty. An atom in an excited state does not decay at a fixed moment, but only with a certain probability over time. The precise instant when it will emit a photon and drop to a lower energy state is unknowable in advance. This randomness is not a flaw, but a feature woven into the fabric of existence. The strangeness deepens when we consider the phenomenon of quantum tunneling. In the classical world, a ball cannot pass through a hill unless it has enough energy to climb over. But in the quantum domain, particles can sometimes pass through barriers they seemingly have no right to cross. This is because their energy is not a single, sharply defined value, but a spread, a cloud of possibilities. With a certain probability, a particle can be found on the other side of the barrier, as if it had borrowed energy from the future, only to repay it in the next instant. This is not just theoretical fancy, it is the mechanism that allows the sun to shine, as protons tunnel through the energy barriers in the heart of stars, fusing to form helium and releasing the energy that warms our days. Even the very vacuum, the emptiness between the stars, is not truly empty. Quantum mechanics tells us that it seethes with virtual particles, flickering in and out of existence, borrowing energy for brief moments, only to vanish before they can be observed. This zero-point energy is the restless background hum of the universe, the consequence of uncertainty, a residual energy that can never quite be eliminated. As we dwell on these paradoxes, energy becomes less a substance and more an abstraction, a kind of accounting, a tally of what is allowed and what is possible, governed by the strange rules of the quantum world. And yet for all our mathematics, for all our elegant theories, energy remains elusive, its essence just beyond our grasp. There is a haunting beauty in this. The quantum world is not a place we can visit, only one we can infer from its shadows and echoes. Every leap, every emission, every act of transformation is an act of translation from the language of probability to the world of experience. We see the consequences, the colored bands of a spectrum, the sharp lines in the light from distant stars, the glow of a fluorescent lamp, but the mechanism itself remains hidden, a dance of possibility behind the veil. Even the act of counting energy can be fraught with difficulty. In the classical world, we can measure the energy of a falling apple or a spinning wheel with precision. But in the quantum world, the energy of a system is often spread across multiple states, entangled with other properties, accessible only through indirect means. Sometimes the very act of measuring the energy changes it, collapsing a spread of possibilities into a single outcome, never to be reversed. This is the paradox of energy in the quantum realm. We know it by its effects, by the patterns it leaves in our instruments and the predictions it fulfills. But the thing itself, the essence of energy, remains a mystery, a concept both indispensable and intangible. And so, in the quiet hours, as the world slows and the mind drifts, one might pause to wonder at the sheer strangeness of it all. The warmth of your hand, the light from a distant galaxy, the gentle hum of a refrigerator, all are woven from these quantum threads, each event a leap across the chasm of possibility. Energy is the currency of change, yet in the quantum world every transaction is a gamble, every outcome a roll of the cosmic dice. As we leave this realm of flickering uncertainty, of leaps and limitations, we find ourselves drawn onward toward the third act of our journey. For if energy is the thread that binds the world, how does it shape the grander patterns, the flow and transformation of matter, the ceaseless dance of entropy? The quantum world whispers its secrets, but the story of energy is far from complete. It beckons us onward into deeper mysteries. In the long twilight between intuition and knowledge, humanity has always faced the same puzzle. How do we know what cannot be seen, touched, or counted directly? The very notion of energy, ever shifting and elusive, presented itself as a force both everywhere and nowhere, a silent actor on the stage of reality. And yet, through centuries, the search to unmask its workings has shaped the arc of science, drawing forth some of the most imaginative and determined experiments ever conceived. Night after night, through the hush of laboratories and the thunder of colliding worlds, the quest to detect the undetectable has unfolded, a tapestry woven from candlelit chambers to vast tunnels beneath the earth. Let us turn our gaze to the world as it appeared to those first seekers, centuries before the language of physics had found its form. In the early 17th century, Galileo Galilei, with his keen eyes and restless mind, began to tease out the secrets of motion. In the dim corridors of Florence and Pisa, he rolled spheres down gently sloping ramps, attentive to each whisper of movement. With nothing but inclined planes, pendulums, and his own pulse to count the passage of time, he noticed, slowly, inexorably, that falling objects gained speed in a regular, predictable way. Energy, though unnamed, was at work. Galileo's experiments were an act of quiet rebellion against the dogma of his age, an insistence that the truth of nature could be coaxed out by careful observation, not simply deduced from ancient texts. He did not know the full mathematics of energy, but in the steady acceleration of a rolling ball he glimpsed a hidden constancy beneath the apparent chaos of movement. It was perhaps the first modern hint that something persistent, something conserved, lurked behind the outward transformations of the world. The centuries that followed were marked by minds ever more attuned to these invisible threads. The 18th century dawned with the rise of the steam engine, a clanking, hissing marvel that made heat do work, and thus drew attention to the mysterious commerce between fire and motion. The great French engineer Sadi Carnot, pondering the efficiency of engines, imagined an idealized cycle of heat and work. In doing so, he laid the groundwork for the science of thermodynamics, the intricate grammar by which energy and its transformations could finally be measured and understood. But how does one measure something as intangible as energy? The solution, as ever, lay in invention, of instruments, of methods, of ways to trick nature into revealing her secrets. One of the earliest such tools was the calorimeter, a vessel designed to capture and quantify the heat released in chemical reactions. In the hands of Antoine Lavoisier and Pierre-Simon Laplace, the calorimeter became a window into the invisible. They placed a guinea pig inside a chamber packed with ice, measuring the amount of water produced as the ice melted from the animal's body heat. It was a strange, almost whimsical experiment, but from the slow drip of meltwater they inferred the equivalence between the heat of life and the energy released by burning fuel. Elsewhere, in the shadowed workshops of England, James Prescott Joule set out to prove a different correspondence, that mechanical work and heat were but two guises of the same underlying entity. With an apparatus of weights, pulleys, and a carefully calibrated paddle wheel submerged in water, Joule demonstrated that the fall of a weight, its ordered descent, could be converted with methodical regularity into the random agitation of water molecules, its temperature imperceptibly rising. The numbers matched. The energy expended lifting the weight reappeared as warmth, as if nature herself kept a perfect ledger. With each turn of the paddle, Joule's experiment pressed the notion of conservation into the physical world. Energy, though mutable, was never truly lost. As the 19th century unfurled, the idea of energy as a universal currency, transmutable but never destroyed, took firmer hold. It was a time of feverish curiosity as physicists turned their attention to electricity and magnetism, to light and sound. Michael Faraday, in his cluttered laboratory, spun coils of wire and watched needles twitch, revealing the dance of electromagnetic energy. James Clerk Maxwell, with equations that seemed almost magical in their unifying power, showed that light itself was a rippling wave of energy traveling through the fabric of space. But as the frontiers of knowledge expanded, so too did the challenge of detection. The energies in question grew smaller, more fleeting, more deeply buried within the structure of matter. The tools of the trade grew ever more ingenious, matched only by the resolve of those who used them. At the dawn of the 20th century, a new puzzle emerged, the quantum world, where energy ceased to flow in a continuous stream and instead arrived in discrete indivisible packets, quanta. The German physicist Max Planck, seeking to explain the spectrum of light emitted by heated objects, proposed that energy was not infinitely divisible, but came in tiny increments, each one proportional to the frequency of the light. This radical idea, at first a mathematical trick, would soon upend the foundations of physics. Yet how could such minute packets be detected? In 1905, Albert Einstein, inspired by Planck's quantum, explained the photoelectric effect, the way that light striking a metal surface could liberate electrons, but only if the light's frequency was high enough. He reasoned that light itself must be made of quanta, later called photons, each carrying a precise amount of energy. Experimentalists, armed with metal plates, evacuated chambers, and the most sensitive electronic detectors of their day, confirmed Einstein's prediction. The apparatus was simple in principle: shine a beam of light onto a clean metal surface and measure the current of electrons set free. If the energy of the photons was sufficient, the electrons leapt across the gap. If not, nothing happened, no matter how intense the light. The quantum nature of energy revealed itself in a moment of all or nothing, a silent leap, a sudden spark, a new truth. As the 20th century advanced, the scale of experiments swelled. The unseen realms to be probed required ever greater energies, ever greater precision. The search for the atom's inner structure drove scientists to devise the first particle accelerators, machines that could hurl subatomic particles at each other at tremendous speeds, allowing the ensuing collisions to reveal the tapestry of forces and energies at play. The cloud chamber, invented by Charles Wilson, was one such marvel, a vessel filled with supersaturated vapor waiting for the passage of a charged particle. When one zipped through, it left a trail of condensation like a fleeting comet across the night sky. Each track was a silent testimony to the energy carried by the invisible, a proton, an electron, a cosmic ray from the far reaches of space. Later, bubble chambers and spark chambers took up the task, providing ever more detailed portraits of these subatomic dramas. Photographic plates, illuminated by the faintest of traces, captured the evidence for new particles, new forms of energy, hidden deep within the nucleus. With each leap in technology, the ambitions of science grew grander. Nowhere is this more evident than in the behemoth experiments of the modern era. Consider the Large Hadron Collider, a colossal ring buried beneath the fields of Switzerland and France, its tunnels stretching for 27 kilometers. Here, protons are accelerated to near the speed of light, their energies reaching levels undreamed of by Galileo or Faraday. When they collide, the energies unleashed are so intense that new particles, some existing for only the briefest fraction of a second, can be conjured into being, their properties recorded by vast arrays of detectors. The detectors themselves are triumphs of ingenuity, layered like the petals of some immense artificial flower. Each layer is tuned to a different aspect of the collision, tracking chambers to map the paths of particles, calorimeters to measure their energies, muon detectors to catch those that slip through the rest. The data produced is staggering, petabytes of information sifted by algorithms and scrutinized by teams of scientists, all searching for the faintest hints of new energy, new matter, new laws. Yet for all their grandeur, these modern experiments are kin to those of the past, descendants of Galileo's rolling balls and Joule's spinning paddles. They rest upon the same principles, that energy, though invisible, leaves tracks, signatures, consequences. It can be inferred from the movement of masses, from the glow of heated filaments, from the sparks that leap between electrodes, from the showers of particles born in collisions. Not all discoveries have been planned or anticipated. Serendipity, the happy accident, has played its part. In the late 19th century, Wilhelm Röntgen was investigating cathode rays when he noticed a faint glow emanating from a screen coated with barium platinocyanide, some distance from his apparatus. Puzzled, he realized that a new kind of ray, what he called X-rays, was passing through solid matter, carrying energy in a form previously unknown. The discovery, like so many, was the result of careful observation coupled with a willingness to be surprised. Similarly, the cosmic microwave background, the afterglow of the Big Bang, was first detected not by cosmologists, but by radio engineers Arno Penzias and Robert Wilson, who found a persistent hiss in their antenna, a signal that seemed to come from everywhere at once. The energy of the infant universe, stretched and cooled by eons of expansion, was whispering across the cosmos, waiting for a sensitive enough ear to listen. A thread runs through these stories, binding the tools and trials of energy research, the necessity of indirection. So often, energy does not announce itself directly. It must be inferred, reconstructed from the pattern of its effects. Whether in the quiver of a compass needle, the warming of a beaker, the flicker of a Geiger counter, or the showers of particles in a detector, the presence of energy is always mediated through change, through the rearrangement of matter, the alteration of motion, the transformation of light. The ingenuity required to devise such experiments is a testament to the human spirit's blend of patience and boldness. Scientists have peered into the infinitesimal and the immense, crafting devices sensitive enough to register the faintest vibrations, the merest winks of energy exchanged between particles. They have learned to amplify signals drowned by noise, to subtract backgrounds, to calibrate instruments so delicately that the difference between truth and illusion can hinge on a single unexpected fluctuation. Yet for all the triumphs, the quest is never complete. Each new discovery reveals deeper layers of mystery, inviting ever more refined tools, ever subtler measurements. The neutrino, a ghostly particle, nearly massless, slipping through the Earth by the trillions each second, remained undetected for decades after its existence was first proposed. Only with vast tanks of liquid buried deep underground, shielded from the cacophony of cosmic rays, could physicists catch the rare flash of light produced when a neutrino finally interacted. Even now, scientists labor to measure the energy of these elusive visitors, to map their role in the cosmic energy budget. The search for gravitational waves, ripples in space-time itself, demanded even greater sensitivity. The Laser Interferometer Gravitational Wave Observatory, LIGO, with its long arms stretching across the landscape, detects changes in length smaller than a fraction of a proton's diameter, as passing waves carry energy across the universe from distant cataclysms. When, in 2015, LIGO first heard the faint chirp from merging black holes, it was the culmination of decades of effort, proof that even the subtlest whispers of energy could be caught with patience and ingenuity. So the story of detecting the undetectable is one of tools and trials, of setbacks and revelations, from the slow roll of Galileo's spheres to the roaring collisions of the LHC, from the warmth of a melting ice chamber to the silent passage of a neutrino. The pursuit has always been the same: to make the unseen seen, to measure the unmeasurable, to coax the secrets of energy from the fabric of reality. Yet there remain energies yet unmeasured, domains yet unexplored. New puzzles beckon. The dark energy that drives the universe's expansion, the hidden symmetries and broken patterns that hint at deeper laws. The detectors grow ever larger, the questions ever more profound. Somewhere, in the hush between data points, the next great discovery waits, its energy still shrouded, its signature faint and fleeting, just beyond the reach of our most sensitive instruments. As the night deepens and the world slips towards sleep, the legacy of these experiments endures, a quiet promise that, with imagination and resolve, even the most elusive truths can be brought to light. And so the journey continues, the tools sharpened, the trials unending, the triumphs both celebrated and yet to come. In the restless dreams of science, the undetectable shimmers at the edge of perception, always inviting us onward, always just out of reach. There is a hush that settles over the mind when one begins to contemplate the great weave of energy, a hush that is not emptiness but a silent fullness, a pause before infinite possibility. In this gentle hush, let us linger, for we are poised at the edge of wonder, gazing at the filigree of energy that threads through the cosmos and through ourselves, binding us to all that is and all that ever will be. Let us begin with the most intimate of energies, the warmth that pulses in your chest, the subtle crackle of neurons that bring the world into being behind your eyes. Your body is a vessel shaped by eons of evolution, and within it, energy is never idle. With each breath, oxygen sweeps into your lungs, diffuses into blood, and is ferried on crimson tides to waiting cells. There, in the hidden machinery of mitochondria, the energy once captured from sunlight by distant plants is unwrapped and released. The chemical bonds of glucose are pried open, and electrons leap from molecule to molecule, a controlled cascade that powers the beating of your heart, the flexing of muscle, the synthesis of memory. You are, in a sense, a flame, burning slowly, steadily, so long as oxygen and fuel are supplied. But unlike a candle, you do not simply radiate heat and light. The energy within you is marshaled, directed, woven into patterns of staggering complexity. It animates not only your limbs, but also your mind. The thoughts that flicker and flow, the emotions that surge and recede, the memories that anchor you in time, all are manifestations of energy in motion, electrical and chemical, dancing through networks of synapses. The boundary between mind and body dissolves when seen through this lens, for both are currents in the river of energy. Consider for a moment the act of remembering. A scent or a sound barely noticed can ignite a constellation of neurons, summoning forth a childhood scene or a long-lost friend's voice. Each recollection is a pattern of electrical impulses, propagated by the feverish work of ion channels and neurotransmitters. The energy required to awaken a memory is minute, but the effect is immense, a cascade that transforms present experience, coloring it with the hues of the past. In this way, energy is not only the engine of life, but also the architect of meaning. If one were to peer even closer, down to the quantum realm, the mystery deepens. The molecules that make up your body are not static beads on a string, but restless, humming with the zero-point energy of quantum fields. Electrons do not orbit nuclei in tidy paths. They cloud and shimmer, their positions defined by probability rather than certainty. The chemical reactions that sustain you are orchestrated by the push and pull of electromagnetic forces, themselves the result of energy exchanged between particles. Even in the coldest darkness, when classical motion ceases, a residue of energy remains, uncertain, irreducible, inescapable. Yet, if energy is everywhere, it is also elusive. You cannot hold it in your hand, only observe its influence. It is at once the most foundational and the most abstract of all physical properties, defined not by what it is, but by what it does. It is the capacity to cause change, to do work, to set the world in motion. And so we chase its forms: kinetic, potential, thermal, chemical, radiant, nuclear. We map its conversions, chart its flows, and abide by its laws. Foremost among these is the principle of conservation. Energy can neither be created nor destroyed, only transformed. This principle undergirds not only physics, but perhaps philosophy as well. For if energy is truly indestructible, then nothing ever truly vanishes from the universe. The warmth of a summer day, the laughter of a child, the fire of a star, all may change form, disperse, fade, but their essence persists in the great accounting of the cosmos. The sunlight that nourished the wheat, the bread that fueled a poet's pen, the words that moved a nation, each is a ripple in the current, a transformation, an echo that never quite dies. It is tempting, then, to see in energy a kind of immortality. When we die, the organized energy of our bodies is released. Heat dissipates, molecules are reclaimed by earth and air, and the atoms that once danced in our hearts and brains are scattered far and wide. But not lost. The carbon that built our bones may someday rise as a leaf in a forest. The phosphorus that sparked our thoughts may descend into a river, nourishing fish and fowl. In this ceaseless cycling, there is a kind of consolation. We are woven into the fabric of the world, never truly severed, but transformed. This vision, though scientific in its particulars, echoes ancient intuitions. Across cultures and centuries, humans have sensed a vital force that animates the living and the non-living alike, a breath, a spark, a spirit. Today, we call it energy, and though our understanding is more precise, the awe remains. For even when stripped of myth, energy remains mysterious. What is it, truly? Why does it exist? Why does it obey the laws it does, neither more nor less? The physicist's answer is honest and humble. We do not know. We can describe energy, measure it, and predict its transformations with exquisite accuracy. But the reason for its existence, its ultimate nature, remains an enigma. Is energy a substance, a property, a bookkeeping device in the equations of physics? Or is it, perhaps, something even more fundamental, a reflection of the universe's capacity for change. As we ponder these questions, we are drawn outward, away from the warmth of our own bodies and into the darkness between the stars. There, energy writes its stories on a grand scale. The light from distant galaxies, stretched and reddened by the expansion of space, is a message sent across billions of years. The cosmic microwave background, a faint afterglow of the Big Bang, bathes all of existence, evidence of an epoch where energy was everywhere, hot and dense and undifferentiated. In the heart of stars, energy is forged anew. Hydrogen atoms, pressed together by gravity's relentless hand, fuse into helium, releasing light and heat that radiate across light years. This stellar fire is the ultimate source of nearly all energy on Earth, for it drives the winds, stirs the oceans, and feeds the plants that form the base of every food chain. Even the fossil fuels that power our machines are but ancient sunlight, trapped and transformed over eons. One cannot help but marvel at this cosmic genealogy. The energy that moves your muscles was once the fury of a star, the light of a sun, the green alchemy of a leaf. The story of your life is written in energy's script, each chapter a transformation, each page a new arrangement of matter and motion. Yet this story is not without shadows, for energy, though conserved, is not endlessly usable. The second law of thermodynamics, stern and inescapable, dictates that with every transformation, some energy is lost to disorder, to entropy. Heat spreads, gradients flatten, and the universe slides inexorably toward equilibrium. This is the heat death that physicists predict, a time far beyond reckoning when all energy will be evenly distributed and no more work can be done. The stars will have burned their last fuel, the galaxies will drift apart, and the cosmos will settle into a cold, silent dusk. What, then, are we to make of our brief flare of consciousness, our momentary dance of ordered energy? Some might find despair in this vision, a sense of futility in the face of cosmic entropy, but there is another way to see it. For it is precisely against this backdrop of inevitable decay that life's beauty emerges most sharply. To be alive is to be a local reversal of entropy, a pocket of improbable order carved out by the flow of energy. Every heartbeat, every thought, every act of creation is a tiny rebellion against the quieting of the universe. Indeed, the human story is, in many ways, the story of our relationship with energy. From the first campfire to the engines of industry, from the cultivation of crops to the splitting of atoms, we have learned to harness energy, to bend it to our will, to build civilizations upon its foundation. Yet, as our reach has grown, so too has our responsibility. For the energy we use must come from somewhere, and its transformations leave traces, smoke in the air, warmth in the oceans, changes in the climate. This too is part of energy's elegy, the recognition that we are not apart from the world, but entangled with it. The choices we make reverberate outward, altering the flows of energy and matter upon which all life depends. To understand energy is not merely to unlock nature's secrets, but to glimpse our own reflection in its mirror. So, let us return for a moment to the quiet room, to the gentle rhythm of breath and the slow drift of thought. Inside you, energy is at play, ancient and new. It is the spark that quickens the heart, the warmth that soothes the limbs, the fire that lights the mind. It is the inheritance of stars, the memory of sunlight, the promise of transformation. In your cells, in your dreams, in the stories you tell, and the love you give, energy finds new form, fleeting, precious, unique. And yet, as you close your eyes, you become part of a wider current. The energy that sustains you is drawn from the world and will, in time, return to it. Your life is both a singular flame and a wave in a boundless sea, shaped by forces that began before you and will continue long after. The boundaries between self and cosmos blur, and in that blurring there is comfort. For to exist is to participate in the great exchange, to be a momentary arrangement in the dance of energy. The mystery, then, is not that we are made of energy, but that energy can, for a while, become aware of itself. That through the improbable workings of chemistry and chance, the universe has given rise to beings who can marvel at its elegance, who can ask questions, who can dream. The poet's wonder, the scientist's curiosity, the child's laughter, all are ripples on the surface of this ancient sea. And so, as the night deepens and the hush returns, let your thoughts drift outward on the currents of energy carried beyond the confines of flesh and bone. Let them wander to the stars and back, to the first light and the final dusk, to the places where mystery and meaning entwine. For in the end, to ponder energy is to ponder ourselves, fragile, luminous, and fleeting, yet part of something vast and enduring. The journey of energy is not yet over. There are still secrets to uncover, patterns to trace, stories to tell. Somewhere in the quiet between heartbeats, the next transformation waits, silent, patient, inevitable, and with it the promise of new wonder, new understanding, new connection. The elegy of energy is not an ending, but a song without a final note, echoing through the ages, inviting us to listen, to learn, and to dream. As our journey through the shimmering realms of energy gently drifts to a close, we watch its comet tail fading into the hush of space, leaving us wrapped in quiet wonder. May your thoughts float softly on this cosmic breeze, inviting peaceful dreams and the promise of more mysteries to explore when you return. Until then, rest beneath the starlit sky, where curiosity and calm dance together in endless twilight.